Distance and displacement sound similar, but are they really the same? Let's understand motion clearly in just 10 minutes.
Welcome to Teaching Science. Look around you. Literally everything in nature is in motion. From massive astronomical objects spinning in space, all the way down to the blood rushing through your veins. But how do we actually study and describe this huge variety of complex motion around us scientifically?
Think about it for a second. How much distance should we really maintain from the truck ahead of us to completely avoid a collision if it suddenly slams on the brakes? And does that safe distance change depending on how fast we're actually going? Today, we are going to understand this entire chapter step by step so that you don't just memorize it, you actually understand it.
Okay, let's dive into our 6-step roadmap. We've got Introduction to Motion, Distance versus Displacement, Motion on a Graph, Equations of Motion, Uniform Circular Motion, and finally, a quick 1-minute recap. Part 1. Introduction to Motion.
So, before we can calculate anything, how do we scientifically define if an object is actually moving? I know, it sounds super simple, right? But motion isn't just about moving. Scientifically speaking, an object is in motion when its position changes with time, specifically with respect to a fixed reference point or its surroundings. If your position isn't changing compared to that reference point, well, you're at rest. It is literally all about perspective.
Let's actually visualize this. Check out the athlete here. To map her position perfectly as she runs, we first have to lock down a fixed reference point. We call this the origin, marked with an O. But, just having a distance isn't quite enough. We absolutely need direction too. For an object moving in a straight line, it can only really go forward or backward. So we represent that direction using plus and minus signs. Basically, positions to the right of our origin O are positive, and anything to the left is negative.
Part 2. Distance versus displacement.
All right, we're going to clear up one of the absolute most common confusions in Class 9 physics right now. Distance and displacement are totally different things. Imagine our athlete starts at the origin O, sprints forward to a point 100 meters away, and then jogs back along the exact same path, stopping at the 40-meter mark. The total path she traveled, that's 100 meters forward plus 60 meters back, is her distance, so 160 meters. But her displacement? Displacement is purely the shortest net change in her position from the start line to the finish line. Since she started at 0 and ended at 40, the magnitude of her displacement is just 40 meters. Basically, distance is the entire sweaty journey, while displacement is just the shortcut.
Let's check your understanding. Think about this for a second. If you run in a complete huge circle and stop exactly where you started, what's your displacement? Got it? The answer is 0. Yeah, 0. Because your initial and final positions are literally the exact same spot, your net change in position is 0, even though the total distance you ran might be absolutely exhausting.
Part 3. Motion on a graph. Now, physicists don't just use words to describe motion. They use these really powerful visual and mathematical models to show how things change. As you've probably seen in math class, line graphs are the perfect tool here. To track motion, we plot line graphs to show how physical quantities, things like position, velocity, or acceleration, depend on time. Time is usually just ticking away on the horizontal axis, and we watch how the position or speed climbs or falls on the vertical axis. It's kind of like a visual story of the whole journey.
Part 4. Equations of motion. Okay, let's step into the mathematical core of this chapter, the equations of motion. Now, I know formulas can sometimes look a bit intimidating, but I promise we'll break them down into completely logical steps. We're looking at motion in a straight line with constant acceleration. We start off with 5 key variables: displacement s, time t, initial velocity u, final velocity v, and constant acceleration a. From these, we get our 2 fundamental primary equations. First, v equals u plus at. Second, s equals ut plus half at squared. These 2 master equations are literally the foundation for everything else. But what if we hit a problem where we just don't know the time? Well, we can actually combine these 2 primary equations to create a brand new one by completely eliminating the time variable t. Follow along with me here. Step 1, we take that first equation and carefully rearrange it to isolate t. Step 2, we take that new value of t and plug it into every single place we see a t in the second equation. And step 3, we just apply some basic algebra to simplify and rearrange those terms. And when you do that little bit of algebraic magic, you get this really beautiful result. 2as equals v squared minus u squared. This is our third equation of motion. It brilliantly links velocity, constant acceleration, and displacement without ever needing to know the time. Pretty cool, right?
Part 5. Uniform circular motion.
Let's shift gears to our final core concept. So far, we've only talked about motion in a straight line. But what happens in the special case where motion doesn't happen in a straight line at all? To figure this out, let's look at a classic NCRT activity. Imagine you place an adhesive tape ring completely flat on a table, and you spin a marble so it just continuously runs along the inside boundary of that ring. It's moving in a circular path, right? Now, what do you think will actually happen if you suddenly lift the ring straight up while the marble is still moving?
Well, the marble definitely doesn't keep curving. The exact moment you lift that ring and remove the physical boundary, the marble instantly shoots off in a perfectly straight line. Specifically, it takes a straight line tangent to the circular path at the exact instant it was released. This shows us something amazing. An object moving in a circle is actually constantly trying to move in a straight line, but the boundary forces it to continuously change its instantaneous direction.
Part 6, 1-minute recap. We have covered some seriously incredible ground today. It's time to lock in everything we've learned with a rapid-fire summary. Here are your key takeaways. First, motion is always relative. You absolutely need a reference point, or origin O, to even define a change in position. Second, please don't confuse distance, which is the total path length, with displacement, which is just the shortest straight line net change in position. Third, if you have constant acceleration, you can easily connect velocity, time, displacement, and acceleration using our 3 beautiful equations of motion. And finally, in uniform circular motion, if the circular constraint is suddenly removed, the object will fly off in a straight tangential line based on its instantaneous direction. Do you see how beautifully interconnected all these concepts are? Next time you're sitting perfectly still in a moving car, ask yourself, are you actually at rest or just moving perfectly in sync with your reference point?
That's all for today. Keep revising, and for more easy science explainers, subscribe to Teaching Science. If you found this explainer helpful, like it and hit the bell icon for notifications about new explainers. See you in the next chapter.